Okay, so once again, I'm Bradley Evans. This is for CS 260 in the spring quarter, distributed systems programming. So when I tried to do my demo on June 7th, which was a Friday, the system crashed, and I wanted to go ahead and put this video out the night of so that you could see a snapshot of this working as it was supposed to during the demonstration. So what I'm going to do now is go ahead and try to give the demonstration as I intended to during the presentation time during class. So the first thing I was going to demonstrate over here was the minimum example. And it seems that my mouse is being captured on the screen in the wrong location, so we're going to try to ignore that. All right. So this is the minimum example. It's pretty straightforward. Up here you have your initialization block, so we'll go ahead and start off by clearing the output. So Jupyter is a Python notebook. It lets you basically run blocks of Python code interactively, more or less. It's a very good rapid prototyping tool. I know that the algorithms course and I believe CS like 12 and 13 have started using similar structures to teach students introductory programming. In any case, let's go ahead and run this first block. So this first block is going to pull out everything from PyMote, and then it's going to generate a network of a bunch of nodes, about 100 here. So I'm going to actually add in this, and this should actually show us the network. One second, let me pull a snippet of code out from my other example. So as I said in class, there are a number of running compatibility issues with this really old kind of Python implementation that they have going on here. So some things are just going to be slow. So I have to put this in here to address these errors. And there we have our 100 node network. Pretty complicated. It assigns them numbers. Those are unique node IDs to this network. And if I generated another network before, then it'll start from the last network's largest node. So there you have it, a bunch of nodes that we can start playing with. Again, each of these nodes acts as a state machine. So a really basic minimal example here is just a flood algorithm. So really this was just kind of to show the structure of a PyMote algorithm. You import these two blocks in, and then you define your class immediately below. This one could be left blank, but this one's required. So down here, this is the initializer block. This defines our initial state. So for every node in the network, we're going to define that node being the idle state. And then we're going to pick, let's see, an initializer node. And the initializer node is basically going to be some first node that gets this key. And I believe it is defined. So this is fed in, and node 0 is going to get. So what we're going to do is we're going to assign basically, so that what this is doing down here is creating a pointer to this 0 node in the system, and then it's going to put this little piece of information into that node's memory. And then when we run the algorithm with this command down here, simrun, it's going to find the node with some information in it, and then it's going to call that node the initiator. So only one node is going to be the initiator, and that's going to be node 0. And that's basically how it's going to go. I can put multiple nodes in as initiator nodes. So this is what this array is. I can set up a bunch of initiator nodes. And then down here, it's going to send out this initialization message to the initiator node, and then we start. So this is the initialization message. It's only sent once to the initiator node. And then this initiator node is just going to send out that little bit of information and then go to the done state. This is the idle state, which is, of course, the default state most of the nodes end up in. And this is just going to basically, if it receives a message with this header, which is the only message we've defined, then it's going to send. So it creates here a list of all of its neighbors. It removes the message source from the neighbor from the destination nodes, and then it transmits a message containing the information, the message data, to all of those nodes. And then it goes into the done state. So I had alluded to this in lecture, but this isn't a real flood algorithm in that going into this done state means every node is going to only send this message one time, and that's not how it works in the real world. You would most likely be sending this in a loop forever unless you put some controls in to basically stop the messages from going if it gets to nodes that actually have already received the message. So I was hoping to be able to invite the students to let me comment out the line I just commented out, that node status done, and then talk about right there on the spot, how do we improve this flood algorithm, what states should we add in, and then we could add the states in right there on the screen. But demos being what they are, I didn't get to do that. So what we're going to do is run this real quick in its native state. So I have to run this node to instantiate the class, run this block, and then run this block to actually initiate the simulation. After step 32, all nodes are in the done state, and then I can go ahead and print out the contents of each node, and then I have my hello world. This is to show some of the structure of the net object. So if you remember up here, I define net algorithms. This is a tuple in Python. You can actually define multiple algorithms to be running at the same time on this network of nodes. So these can maybe correspond to different consistency levels, or different, maybe you have a leader algorithm and you have a broadcast algorithm, and you want to see how the two of them interact. In any case, point is you have this algorithm thing, this object, and since this is what is contained in here, what I can do is in my initializer, I can actually add a counter So here I'm just going to create a counter for message count real fast, and you can see how fast these systems are instrument. And this is going to create a counter that ticks every time you send a message. We're going to see how many messages this takes. So let's run the simulation one more time. Whoops. I need to rerun this node so that my changes get saved, and then run the simulation. So it finishes the same amount of time, not surprising. All right, not surprising. So once again, in here, you now see this message count variable. So I can run this and see that 1,331 messages were sent to deliver a broadcast message to 100 nodes. Not super efficient, but not awful either. And then I can hit reset on this to go ahead and show the to restart the simulation completely. So what this command here does is it runs a GUI, and let me see if I can pull the GUI up on the screen. I need to add my VMware client to this screen capture software I have running. All right. So up on the screen, you should see a VMware window, and what happens when I run this line in the Python notebook should be that a small GUI window appears. And it looks like it's still running. It must be stuck on something. Stop my kernel. All right, kernel's interrupted. So actually that window you're seeing is where the kernel is actually running. So what I have to do right now is clear this error, and now I should be able to run this GUI. And sorry about the delay. Okay, kernel restarted, so run then. Okay, well that doesn't seem like it's going to work today. So we'll go ahead and abandon that for now and move on to the next part of the demonstration. So I'm going to go ahead and restart and clear my kernel so that this next portion behaves. I'm going to restart and clear my kernel here too. All right. So once again, initialization block up top. I'm going to use a slightly smaller network to demonstrate a leader election algorithm. So go ahead and run that first block. So this is my really naive implementation of a leader election algorithm. Here's our network that we're going to be acting on, randomly generated. So like I said, it's really naive. What this is going to do is some initiator node is going to say, hey, I'm the leader. It's going to, first off, all the nodes are going to think that they are the leader. One node is going to be an initiator. The node is randomly selected. And I believe that I have the random selection in here. So this is the node I'm going to use. And this initiator node is going to initiate a leader election by sending a leader update packet to all of its neighbors. If you do not define a destination by default, it sends it to all its neighbors, containing the node in its memory for leader, which at this point is just going to be itself. So from there it goes into an idle state. And this idle state is going to say, if I receive a leader update, then if the message contains a leader with a lower ID than me, then I will change my leader memory object in here to what's contained in the data, which is a node. And then I will broadcast that to all my neighbors. Otherwise, what I'll do is send my own node to everybody, which is going to send my own leader to everybody, which is ideally going to be a smaller node number than what was contained in the message. So sounds fairly straightforward. Makes sense to me logically. Let's run it for, we'll just add 1,000 steps in here and see what happens. So this will go on for a while, and you would think, you would assume, if you're naive, haven't really reasoned about these systems extensively, that what you have there is a fairly solid little algorithm. But of course, the leader election problem is not so trivial as that, and running this simulation makes that abundantly clear. So we're at about 500 steps. I can always instrument this with status messages, whatever I need, so that I can observe the progress of my algorithm, which I do to greater effect in the next algorithm. All right, we're still chugging along. You notice in this one I didn't use the done state. I wanted them to kind of react to all their messages at all times. And I just want to see what happens down here if we've actually reached convergence after 1,000 steps. We're still going, we're almost at the end. All right, so after 1,000 steps, we've got a bunch of nodes. Remember, this is just a 20 node network. A bunch of nodes recognizing node 1 is the leader, quite a few. 1 seems to be the winning side right now, but even after 1,000 steps, I've got 6s, I've got 4s, I've got 2s, I've got 3s. I don't see any hundreds or thousands, but you can also kind of look up at the topology and make sense of this. So I've got 6, 4, and 3, and 2. And 6 is down here. 4 is right here. So these being neighbors is kind of interesting that some nodes are seeing them as leaders. 3 is right here, and 2 is right here. This is interesting. It's not what I expected. I expected these to be kind of out on branches. But yeah, they're very well connected nodes. So you wonder if that has something to do with why the messages are propagating that way. But 20 nodes, 1,000 steps, probably tens of thousands of messages, and we still do not have consensus. So I'm hitting close to 20 minutes now, so I'm just going to quickly go through the next thing. So now that you kind of understand the syntax, I can show you what it looks like when you do a crash. So here's a leader election with a crash. I call this a dice roll, and I say that if it, well, I should go to the idle state first. I give the node a 1 in 100 chance right here of crashing, and then I just define a state. That's my crash state. And if it receives any message at all in the crash state, it will notify that sender it's crashed to simulate the sender noticing that it's not getting any pings back from the crashed node. So basically assuming that the node has perfect crash detection. The network has perfect crash detection. So then I allow the node to recover, and then I assume that when a node will know that it's recovered and can send a message to its neighbors that, hey, I'm back on the network, what did I miss? And then you can start incorporating some of that in. So I didn't really change the leader election algorithm much. I just integrated the crashes. And if you want to run this, and now you can see my debug messages in here showing crashes, and the node's attempting to recover from those crashes. So this is running for a shorter duration, 500 steps versus 1,000 we just ran. All right, great. So now we still see that we have more or less the same kind of distribution. There's no 6s in this one, but yeah, still don't have consensus, 500 steps with crashes. Moving on. Trying to get to a better, you can really see the iterative process when you kind of put your algorithms in this way. So here's me attempting to do a yo-yo algorithm. The yo-yo distributed algorithm is described here in Wikipedia and also in a paper from, I believe, 2007. More or less, so total reliability, no message lost in transition, bidirectional, initial distinct values. These are all assumptions we can make with PyMote, and then the algorithm is described here. So in the leader election, I basically try to implement that. I create some memory to record certain substates. I have an initiator state that puts everybody in the awake phase corresponding to, let's see here. So this is the pre-processing phase, and this is the awake state where it's described here. So it's going to start trying to orient itself. So in the awake state, it's going to try to pull all of its neighbors and figure out if it's a local minima. All right, so right here it's doing all of that, and then once it gets enough respondents, it decides if it's a local minima, if it's a sink, and then it will go ahead and move into each of these states. So since I have more states going, a good time to go down here and show where the status is. If the state defined in node.status, whatever state that is, it's going to correspond to this kind of key. So that's the function that's going to run, which corresponds to this right here. So it's getting on to 25 minutes for this video. And what I'm going to do now is just kind of run through. So here's a source. a source node, it's going to basically send out its candidacy to all the nodes around it. You've got edge directions marked by storing outgoing nodes in this memory location, and then there's an incoming one that corresponds. So this is a much more complex sort of algorithm, and let's just go ahead and run it without getting into the nitty-gritty of, oh, I should stop this because I put way too many simulations in here. So you would think that this would converge, but you can now start seeing some of my debug code in here. Help me visualize what's going on, and I can see that a lot of these are kind of stuck. It takes a long time just to reach a point where most of the nodes have gone out of that awake state. And I'll notice that messages from the awake state, so this source candidate message is associated up here with the awake state. They're kind of gumming up the works because they're not being processed, because the only state that I initially, so here's source candidate. I wasn't actually processing source candidate messages outside of the awake state. So those kind of sit in the inbox for a while. So it just kind of goes to show that you have to kind of account for slow nodes that don't get the memo fast enough, or you need to make those nodes a little bit more robust. Okay, so you're seeing the debug messages I'm having. I think that the point of all the things I've been showing you is not to say I have a great way to develop leader algorithms. I know that this leader algorithm isn't very well implemented. Okay, we finally get our results down here, and you can see that it doesn't. My implementation doesn't converge very well. The point is that this was, without a lot of documentation, pretty hard to wrap my brain around. But now that I understand how the system works, it really helps me really understand and visualize how these algorithms are put together at a high level. It strips away all the layer 2 and layer 1 stuff that can really take away or confuse, and lets you just deal with the algorithm as it's written in an academic paper. And I think that's very powerful if you're, for example, an educator trying to have a platform in which to assign work related to an algorithm, or if you are a tinkerer just trying to think of maybe an IoT device or a mesh, some kind of wireless mesh networking setup for some gadget you want to build. I really think that this is an excellent prototyping tool for a distributed network, and I think it really could have applications in education and at the entry level of getting programmers into distributed systems programming. I hope that makes up for my my crashed demo earlier today. I know that this went way longer than it should have for the demo, which was a half hour during the class period. But I hope this helped, and that concludes my presentation. Thank you.